Prakash, happy birthday once again. We celebrated it already earlier this year in the Caribbean, which was very nice. I'd like to wish you all the best, also to Laurie. And I'd like to acknowledge very clearly your inspiration to me, I think, for the whole community here. And I certainly am happy to honor you with this presentation, which is inspired by what you've done. I'll talk about quantum logic, categorical quantum logic, and I'm trying to get to reach an axiomatization of this area. I'll do this by successively imposing a number of assumptions, which I'll describe separately. So the aim for me is to extract the essential properties, especially in relation to classical and probabilistic logic, what is typically quantum. And my idea, and what I set myself as sort of a goal, is to find what could be a quantum topos. Now, I don't know what a quantum topos is, but maybe in the end we find out this category, we all recognize that should be called a quantum topos. So I'm putting forward some assumptions for it. The logic will be used on effect modules, structures I've been studying for a couple of years now. I will not be able to describe them in detail here. Phil Scott will talk about that later, but I'll give you an idea of this. And let me be clear, it's not finished framework, but for assumptions, and I'm happy to receive feedback on this. What are my main examples? First, the category of sets for classical logic. Then I'll use the Kleisli category of the distribution monad for probabilistic logic, but you can also use the Kleisli category of the Jury monad, although I will not discuss that in detail here. Then the category of C-star algebras with unit of positive maps, and you can use some variations, but I will not discuss these variations. But actually in this category of C-star algebras, seeing this as an example, that involved on my side three in itself trivial mental steps. The first one is not to use in this setting Hilbert spaces, but C-star algebras. And the second one is to use the opposite of the category of C-star algebra. And the third one is not to use the standard star homomorphisms, but unit of positive maps. Now these three trivial steps took me roughly 2 years to read, to see that these were crucial steps, and I think this is helpful. But there are other categories that satisfy at least some of these assumptions and can be useful in this setting too. So let me come to my 4 assumptions. The first one is about basic categorical structure, and it is I require in my category a final object 1, finite coproducts, and they satisfy some elementary properties. Now, you don't need to remember those properties in detail. They're fairly basic. They hold in all toposes and in effect in all categories with universal coproducts. They're fairly mild, but there are also some examples where they don't hold, specifically Kleisli categories of the power set monad. So in a non-deterministic setting, especially the jointly monic property does not hold. I'll do some definitions. So I have a final object 1. If I take the n-fold coproduct, I'll write this as n dot 1, and tests in my setting are simply maps from x to the n-fold coproduct. I call them m-tests. And a predicate is extremely simple. It's a maps from x to 1 plus 1. And I'll write 1 plus 1 also as 2. And these are typically classical predicates. So you might think they're boring, but it turns out they're reasonably interesting in several instances. So I get for free some structure on these categories. I'll take the 1 predicate, it's the first co-projection, the 0 is the second co-projection. This is completely arbitrary choice. And I'll take the ortho supplements, P per, as swapping the two values. And what you see immediately is that I get a classical logic, P per is P, and these properties are rather trivial. But indeed, in a quantum probabilistic setting, you typically have classical logic. The predicates on 1, so the maps from 1 to 1 plus 1 are called scalars, and they carry a simple moment. Let's see some examples. In sets, of course, the maps to 1 plus 1 are the usual predicates. Things become a bit more interesting in the classic category of the distribution model, because maps from x to 2 correspond to functions from x to d of 2, and d of 2 is the 0, 1 unit interval. So what we get here are fuzzy predicates from x to 0, 1. So suddenly you have a bit more structure. It looks as if you start with simple things, but it becomes a bit more interesting. Even more so in the category of C-star algebras. The complex numbers are initial in the category of C-star algebras. So if I go to the opposite, they are the final object. So I can write them as 1 there. 1 plus 1 there is then the Cartesian product, C squared. And I get this correspondence. Maps from A to 2 in C-star op correspond to maps from C squared to A, which are positive in unison. And you see with the little calculation that these are effects in the C-star algebras. These are positive elements below the unit. They're on the unit interval inside the C-star algebra. These things are typically used as predicates in quantum logic. So again, they arise as maps into 1 plus 1. A proposition is that the predicates have the structure of an effect module. Given the simple assumptions I have on a coproduct, I can already prove this. And the scalars you have are the predicates of 1. Even more, this yields a nice functor. It's factorial, so I get a category from B to effect modules and opposite. This functor satisfies some nice categorical properties to preserve some structure, but that's not so important at this stage. And in effect modules or effect algebras, you have a partial sum. I'd like to briefly describe to you how you get to this partial sum. So if I have two predicates, I define they are orthogonal if there is a bound not going into 2 but going to 3, 1 plus 1 plus 1, which sort of combines P and Q in a uniform way. And as you may remember from the requirements I had of coproducts, these two maps were required to be jointly monic, which implies that there is at most one such a bound. If I have such a bound, I'll define the sum P plus Q. I'll use this notation for the partial sum as postposition with the codiagonal, which collapses these two elements. Now this all behaves very nicely and gives the structure of an effect module, which is an elementary algebraic structure. More importantly, the tests can also be described in this setting. So tests are maps to the N4 coproduct. They correspond to n separate predicates, which add up to 1. Now, apart from effects, which are predicates in this setting, you can also describe states. A state on an object is simply a map from 1 to x. For a predicate and a state together, I define a validity predicate, omega satisfies P, which is simply the composition P after omega, which goes from 1 to 1 plus 1. Remember, these maps are scalars, which are probabilities. So this gives the probability that such a predicate holds in the state. And you can prove that the set of states is a convex set and is closed on the convex combination of the scalars that you have here in abstract form. You can also, there are also ways of putting some elementary topological structure on them, but I have not elaborated that in detail. Let me see some examples. So in the set theoretic case, remember, a predicate is just a subset and a state is just an element, so this is the usual form of validity. In the probabilistic case, a state is a distribution on such a set, P is a fuzzy predicate, and the validity is then this sum, which is an ordinary probability calculation. In C-star algebras op, states are mapped from A to C. Remember that things have to be turned around and that the complex numbers are the initial object in C star algebra, so things turn around. This is the traditional formulation of states in the theory of C star algebras, and it's just a function application to get a probability here. So you get a uniform description at a very high level. So what do I have? I have in this language states, programs and predicates. States are points of an object, programs go from x to y, and predicates are maps going into 1 plus 1. And each program gives a state transformer mapping states on x to states to y in a forward sense, but also a predicate transformer acting backwards on predicates on its codomain to predicates on its domain. And this may be called weakest precondition. And there is a Galois style equation that holds in this case that f lower star of a state satisfies q that has the same probability as omega satisfies f star of q, which is simply this composition. So that works out fairly smoothly. So what is the summary so far? Recall the first assumption was I have a final object, I have co-products which are slightly nicely behaved. And from this I get a structure like this. So I get a functor, a predicate functor going into effect modules, a state functor going into convex sets, and there's an adjunction between these two which exists for very general reasons. So it's quite a bit of structure already from fairly weak assumptions. You can wonder, does this commute? Going like this, is that the same as that? In general, not. My assumptions are too weak for this, but you do have natural transformation, like this and like this, and they're actually given by this validity relation, the natural transformations. So the validity is a deep part of this kind of categorical structure. Good. I'll come to my second assumption, which is about measurement. The measurement assumption says the following. If I have a test, an n test, so a map going to n times 1, there is a measurement map going from x to n times x. So notice that I can place the 1 by x here, and it satisfies the assumption that if I annihilate these x's by taking the unique map to the final object, then this commutes. And there should be some additional conditions which I'm skipping at this stage. And what's interesting, in this case, if I have an effect, I can take such a measurement map, which goes into the n-fold co-product, and I collapse by taking the co-diagonal. I get a map from x to x. And the question is this the identity? Well, that needs not be the case. And typically this is the side effect of the text or of the predicate. And one of the interesting features of this approach is, I think, that these side effects appear very naturally in the framework. Some examples. An n-test in a category of sets is a collection of disjoint subsets on X. And if I have such a disjoint cover, I can define a map from X to the n-fold co-product by simply going into the different co-product options depending on whether my element that I'm working on is in one of these predicates. In the Kleisli category case, I can basically do the same, but I take a probabilistic combination of these selectors and the different co-product options. This is reasonably straightforward. In the C-star algebra case, things become a bit more complicated because of the opposite. You have to turn everything around. So an n-test consists of a collection of effects which sum up to 1. They should give a measurement map from A to the n-fold co-power in C-star op. So in C-star itself, in the other direction, it becomes a map from the power, n-fold power to A. And it can be defined in this way by P and post multiplication with the square root of these effects. And what's interesting is that these side effects, they occur not in sets, not in the probabilistic case, also not in the C-star algebra case, but only if the C-star algebra is commutative, which is sort of what you expect. Right? That in the commutative case you don't have this phenomena. I can also then go towards a language for working in these categories, towards a programming language. So suppose I have a test P, I can write P question mark and then options, and options of programs, which I can interpret in the following way. First I measure, I get all these options, and I do the code tuple which selects these kind of options. And in a more programming style, you can write this like this. You do a test, there are n options, and corresponding to each of these options you do a certain program. But interestingly, in this case, these PIs may have a side effect, at least in the quantum case. So in the set theoretic case, it's just exclusive OR of these kind of things. There's only one option valid, and then you follow this one. In the probabilistic case, you have a probabilistic combination of these things according to these predicates, and in the quantum case, you have a quantum combination which may have a side effect. A basic result in this setting is that an effect, so a predicate in this setting is side effect free in a C-star algebra, if and only if it's in the center of the C-star algebra. So it commutes with everything. And that's just a sort of basic result, I guess, a sanity check. It's something that you would expect for such a framework. Even stronger, you can show that the C-star algebra is commutative if and only if all its effects are side effect free in this logic. Good. Even more, you can not only define test programs, but also test predicates. So given two predicates, P and Q, I define this logical formula, which you can think of as test P and then Q. So what I do is, I measure P. In the first case I do Q, and in the second case I do false P. So which basically excludes the second case. You can also allow the second case, which is P, test P, then Q, where you put a 1 here for the true predicates. And you can then call your model commutative if these two commute, and you can talk about projections in the subset setting. Let me go through the examples quickly. In the set theoretic case, the test, the and then test is conjunction, and the then test is implication. So this works out nicely. In the probabilistic case, the AND test gives you multiplication of probabilistic predicates, and in the then case you get this formula, which is known in the literature as Reichenbach implication. So it's known in probabilistic logic. And in the case of C-star algebra, if you elaborate this formula, you get square root E times D times square root of E, which is a formula which already appeared in work of Stan Goodder, who tried to axiomatize sequential effect algebras. And this is the implication version that comes with it. So there's a very general approach which gives this sort of natural logical structure in different instances. These test predicates satisfy some standard logical results. For instance, they preserve this sum in the second coordinate, they preserve scalar multiplication. We call this as a quantitative logic, so this all works well. And we even have the Morgan formula for these two, so things work out well. And as an example, you can use this for weakest precondition reasoning about these test predicates. So if you do weakest precondition of this test program for this postcondition, you get this formula. It's a bit difficult to read, but there's a very strong formal similarity with the weakest precondition rule for the if-then-else, which says P and the weakest precondition of Q, which is here test P and this, or not P, test this one, and the weakest precondition of F2. that's really a strong similarity. Interestingly, you can talk about pure maps in this category. The pure maps, still in very abstract form, are the maps that commute with all measurements. Right? And recall measurements can have side effects, so this commutation is not trivial. And these pure maps then can be pulled through these formulas via substitution. And interestingly, in the set theoretic case, all maps are pure. In the probabilistic case, the maps are pure, which come from functions in sets, which are really non-distributive in a certain sense. They are also called the pure maps in a functional programming setting. And in the category of C-star algebras, the pure maps are the star homomorphisms. So the maps which also preserve the multiplication. My third assumption is presence of some tensor structure. So the categories should be symmetric monoidal, have tensors. An important thing is that the final object is the tensor unit, in this case. And the tensor distributes over coproducts, and then there are some coherence requirements, which I will not go into. But the tensor should also interact appropriately with measurement maps. In the presence of these tensors, certain things suddenly become commutative, a certain monoid structure that you have there, which is fairly standard. And with these tensors you can start pairing predicates, but you can also pair states. And this allows you a certain level of modularity in your reasoning. So a paired state satisfies a paired formula if and only if, or what comes out is simply the product of the individual results. Because the final object is the tensor unit, you get projections in a standard way. There are no diagonals, of course, in the quantum setting because of no cloning, but projections you have. And these projections give rise to maps between predicates as predicate transformers and state transformers. And here they can be understood as weakening, so moving a predicate to a larger context. And this operation here on states is usually known as calculating a marginal or a partial trace. And it arises in this very abstract setting. So we have this pairing and disassembling of states, and you can wonder, do I get an isomorphism in this case? Well, that's the case in set theory. But in general, it's only retraction. If you have two separate things, put them together and then deassemble, then you get the originals back. In a probabilistic case, it's a retraction because joint probabilities may involve dependencies, and in the quantum case, it's precisely because of entanglement. And these two are related in this sense via tensors. The fourth assumption is then fairly standard. It should be an object which supports qubits in a certain way. There should be an up and a down qubit and an associated predicate which behaves in a certain way. Let me finish with a small example, just I'd like to flash it to you. The superdense coding. It's a standard algorithm that allows Alice to send two classical bits to Bob by transferring her part of the shared entangled bit. And as a map you can describe it like this in this setting. So 4 is 2 times 2, so those are the two classical bits. By initialization you get 2 quantum bits. Alice does some test on her part of the quantum bit, transfers the things to Bob, and Bob can do his own test on the whole space. What comes out is again 4 out of this test, and correctness says that this must be the identity. In this language that I get, it can be described in such a way. And hopefully this is a reasonably intuitive language. So here you do initialization, you show 2 up bits, you do Hadamard and a conditional not on them, then you get B1. Alice does a test on the input, which are the 4 classical bits of information, and depending on the outcome, she does certain things on her part of this initialized state. Then control transfers to Bob. Bob can do his test, and these are the Bell state test operators. And on the basis of this test, he outputs 1, 2, 3, or 4. He throws away the rest of the state, so there's projection involved here. And a challenge is to prove that this program is at a logical level, using weakest precondition reasoning is correct and does what it should do. So let me come to my conclusions. I think these effect algebras and modules, although I haven't described in detail what they are, they're fairly natural structures. They arise in many examples, but also they arise very naturally from categorical constructions, which is maybe the more surprising bit here. Then these triangles of effect modules and convex sets, I think, capture some essential aspects of program semantics. And I think these 4 assumptions capture some essential aspects of quantum logic, but I don't want to claim this is the definitive picture. I think more examples, constructions, closure operations are needed to finish this. And I'm certainly also interested in the logical aspects of this. And a postdoc of mine, Robin Adams, will talk about that in a few weeks in Kyoto. Thank you very much for your
my exam at the end of the day. So, well, I've listened to 4 hours of your talk, so
yeah.
It's hard to ask you questions, but nevertheless, perhaps you could contrast your approach to quantum logic with the categorical quantum logic being done by Bob and Bob's Samson and Peter and others here at Oxford, where the compact closure property is very important.
Yes, yes. I don't have a full answer to this. I think the approach is somewhat different. I'm more focused in the end on actually calculating things, calculating probabilities of programs. Maybe people will say not, so they'll do that as well. But precisely where compact closure plays a role is not so clear. Because I'm working in a C-star elsewhere context. What that translates to there, I've been thinking about this, but I don't have a clear answer.
You probably don't have it, right? Because you want to do infinite dimensional things.
Yeah. So far, I haven't had to restrict myself in any way to finite dimensions. I have been using finite tests, so n tests, but this can be generalized relatively easily because these n tests of mine are functions from the natural number n to effect modules. And this can be generalized to sigma algebra, and you can use a similar approach there. Yeah. So, yeah, maybe this is more general and doesn't depend on quantum, on compact closure. Remains to be seen.
No, it's not my talk. Any more questions?
So you gave the pseudocode for superdense coding. What's the status exactly of that? So you've written this down. Can you interpret this formally in a setting that satisfies your...
Yeah, I can. I've done the calculation, interpreted it in a category of C-star algebra. So then it becomes a map from C4 to C4.
And in that setting it does the right thing, it gives the identity. But you're saying you don't yet have a logical proof of that? Or
no, I haven't done it at the syntactic level.
Right.
So Robin is developing a purely syntactic algorithm. He's looking at what I have semantically, incorporating that in the logic, and then he wants to check if his logic is sufficiently complete to do this protocol and many others.
Yes.
Yeah.
You're finding an internal language?
Yeah, it can be seen as an internal language. Yeah, definitely.
Here you can see that you actually put the cups in by hand with your bell states.
Yeah. And that is good or bad, or what?
I don't know.
Oh.